At the beginning of time, the universe made a choice, one it was never meant to make. Matter and antimatter were created in perfect balance, destined to meet and vanish, erasing everything before it began. According to the laws of physics, that should have been the end of the story, but something broke, just slightly. One particle in a billion slipped through the cracks. And that anomaly became everything. Every star, every planet, every breath you've ever taken, all of it, born from a cosmic betrayal of symmetry. This is not just a story of antimatter, it's the story of why anything exists at all, and how close it all came to not existing at all. They say the universe began with a bang, a single unfathomable moment when time, space, and energy erupted from an origin point so small it defies comprehension. But there's something they rarely tell you. The universe should have ended almost as soon as it began. Every law of physics we know, every equation etched into the chalkboards of brilliance, tells us this. The Big Bang didn't just create matter, it created antimatter too. Perfect opposites, particle and antiparticle. A cosmic symmetry so absolute, it was destined to fail. Because when matter and antimatter meet, they don't argue, they vanish. Annihilation, total, mutual, erasure, pure energy, gone, as if they were never there to begin with. And yet we are here, you, me, planets, stars, the things we love, the things we fear, all born from a cosmic imbalance so small, so statistically absurd, it's as if the universe cheated its own rules just to let us in. This is the story of that imbalance, and of the shadow world we call antimatter. A world that was meant to mirror ours and erase it. But it didn't, and no one knows why. Imagine for a moment the beginning, not the poetic beginning of myth or metaphor, but the real one. A universe less than a second old, blisteringly hot, smaller than an atom, and expanding faster than the speed of light. Within that incandescent chaos, particles flicker into existence like fireflies in a furnace. For every electron, an anti-electron, a positron appears. For every quark, an anti-quark. Perfect symmetry. And then, as quickly as they're born, they find each other and vanish. It's beautiful in a way, a celestial dance of birth and death. But there's a problem. According to every model we have, this dance should have left behind nothing but light. The universe should be a dark, cold bath of radiation. No stars, no planets, no physicists to ponder their own futility. But something went wrong. Or right, depending on your perspective. For every billion pairs of particles and antiparticles that destroyed each other, there was one extra particle of matter, just one, in a billion. That tiny cosmic leftover and that rounding error of existence outweighs everything we see. Galaxies, nebulae, the Earth, the coffee mug on your desk, the neurons firing in your brain as you process these words. It's all made of the survivors. But this is not a comforting truth, it's a terrifying one. Because it means our existence is not the product of certainty. It's the product of a symmetry, of something broken, a crack in the mirror of the universe. And we don't know what caused it. Somewhere buried in the earliest fractions of a second after the Big Bang, something tilted the balance. A flaw, a preference, a rule we have yet to uncover. Physicists call it baryogenesis, the mysterious process by which more matter than antimatter came to be. But baryogenesis isn't a theory, it's a placeholder for our ignorance. We have hints, of course, shadows on the wall, equations that almost explain it. But every time we chase it, the trail grows cold. Experiments yield beauty, symmetry, elegance, but no answer. And so, the mystery deepens. But let's step back. What is antimatter really? It's not science fiction, it's not magic. Antimatter is real. It's been created in labs, detected in space, even used in minute quantities in medicine. A positron emission tomography scan or PET scan relies on antimatter. Every time a positron meets an electron in your body, it vanishes in a flash of gamma rays. and that flash gives us an image. But don't be fooled by its utility. Antimatter is lethal to our world. A single gram of antimatter, if it touched a gram of matter, would release as much energy as a nuclear bomb. Not through heat, not through pressure, through perfection, through symmetry. Antimatter is nature's most flawless eraser, and yet it is also nature's most profound clue, a fingerprint on the glass of the universe's creation. It tells us that something should have happened, and didn't. Some theories suggest that matter and antimatter were never perfectly equal, that some unknown field or force biased the production of matter over antimatter. Others propose that antimatter may still exist, hiding in the cosmos, segregated into anti-galaxies far from our own. But if that were true, we'd expect to see the evidence. Cosmic gamma ray bursts where matter and antimatter meet. And yet, silence, a silence so deep it echoes. And so we are left with a paradox. A universe born in perfect symmetry that shattered it. A shadow that should have wiped us out, but failed, not by much, not by a mile, by 1 in a billion. You might be tempted to dismiss it as luck, a fluke, a cosmic coincidence. But in physics, luck is a lazy word. Coincidence is a veil we pull over chaos. And this is not chaos. This is something else, something we haven't named yet. Perhaps it was written into the laws of the universe, an inevitability disguised as improbability. Or perhaps it was not meant to happen at all. Either way it did, and the consequence is you. To understand the shadow, we must first revisit the light. The moment the universe was born was not silent, it was not gentle. It was violence refined into elegance, a singularity erupting into all that would ever be. Time, once non-existent, surged forward. Space expanded with it, not into anything, but creating the very fabric on which everything else would ride. And in that very first heartbeat, in less than a trillionth of a second, something remarkable occurred. The universe began creating, not stars or planets or galaxies. No, those would come much later. What the newborn cosmos created first was potential. Pure, undiluted energy, capable of becoming anything. And from that potential, the first particles emerged, but not alone. Every time a particle of matter flickered into existence, a partner appeared with it. A twin, an opposite, identical in mass but opposite in charge. A kind of mirror image, as if the universe in its infancy demanded symmetry. These were the first pairs. The electron and the positron, the proton and the antiproton, quarks and antiquarks. Together they formed the original binary of existence, not good and evil, not light and darkness, but matter and antimatter. For a fleeting moment it was a perfect system, balanced, predictable, for every step forward an equal and opposite step back, a dance of dualities playing out across a rapidly inflating stage. This symmetry wasn't arbitrary. It was fundamental, baked into the equations that govern quantum field theory and the standard model of particle physics. The laws of nature, it seems, are obsessed with balance. Charge, parity, time, break any of these and the whole machine shudders. But here, in the furnace of creation, the laws held. And in doing so, they created a problem, a fatal one. Because matter and antimatter, when they meet, do not coexist. They cancel, with astonishing efficiency. It wasn't war, it wasn't hate, it was nature folding in on itself. Every encounter between matter and antimatter resulted in mutual annihilation. One particle, one antiparticle, gone in a burst of pure energy, the most efficient conversion possible, and it was happening everywhere. Imagine the scene, a roiling ocean of particles flashing in and out of existence, colliding, erasing, creating again, an equilibrium of fire. The universe was young, hot, and impossibly dense. Energy pulsed at such intensity that matter and antimatter were born and destroyed in an endless loop. This was not chaos, this was precision. But as the universe expanded, it cooled. And with cooling came consequence. The energy density dropped, the fire dimmed, and the fabric of space grew less volatile. Soon, the particles that were being created no longer had the energy to form in large numbers. The creation rate fell below the annihilation rate, and then the erasure began. Particle by particle, the universe began wiping itself clean. The twins that had been created turned inward, seeking each other, cancelling one another out. A cataclysm of nothingness. Had this symmetry held, had the balance remained perfect, that would have been the end, a universe born into symmetry and doomed by it. But it didn't end, because something tipped the scale. We don't know how, we don't know when. Somewhere in the earliest whispers of time, something introduced an imbalance, a flaw, a betrayal of symmetry. For every billion pairs of matter and antimatter that cancelled each other out, there was one extra particle of matter, just one, in a billion. It sounds insignificant, insultingly small, but that surplus, that single survivor for every billion dead, became everything. It's why we're here. That leftover sliver of matter, unpartnered, unopposed, is the very substance of existence. It's the raw material from which stars formed, from which galaxies spun, from which life itself emerged. But it should not have happened. Physicists call this deviation CP violation, the breaking of charge and parity symmetry. It's been observed in experiments. It's real. But it's not nearly enough. The violations we've measured can't account for the vast asymmetry that built our reality. And so the mystery grows. Perhaps there were forces present in the early universe that no longer exist. Hidden particles, now extinct. Fields that rippled once and faded. We call these ideas beyond the standard model, because the physics we know cannot explain the world we see. The laws we have are elegant, powerful, predictive, but they are also incomplete. There's a gap, a crack, a blank space where antimatter's purpose should be. Some have speculated that there may be an entire sector of the universe composed of antimatter, far from us, isolated by the vastness of space. Galaxies made not of hydrogen and helium, but anti-hydrogen and anti-helium. Suns that shine with the same light, but burn with mirrored fuel. If that were true, it would mean that the universe did remain symmetric, but partitioned. That antimatter and matter each claimed their own domain, like rival kingdoms separated by an ocean of vacuum. But there's a problem with that theory. Borders. Where matter and antimatter regions would meet, there should be constant annihilation, and therefore constant gamma-ray bursts, vast streams of high-energy radiation. We should see them in the night sky. But we don't. The silence is deafening. And so, once again, we are left with a single thread. The early universe was symmetric, until it wasn't. And in that betrayal of balance, we were born. You might ask, why does this matter? Because symmetry isn't just an aesthetic preference of nature, it's a foundational principle. When symmetry breaks, new forces emerge, mass arises, time gains direction, entire realities can pivot on the fracture of a single mirror. In this case, symmetry didn't just break, it vanished. And what filled the void was us. As we move forward deeper into the enigma, we'll examine what happened to the rest, to the antimatter that was supposed to balance the books of the cosmos. It didn't disappear, it was erased. Or was it? It's hard to imagine silence louder than creation. But in the early universe, there was a kind of screaming stillness, the silence of things vanishing faster than they appeared. A vanishing act performed across the entire stage of space-time. Every flicker of matter met its mirrored end. This was the Great Annihilation, not a war, not a tragedy. Something colder, more inevitable. It wasn't murder, it was math. The fireball of the Big Bang had cooled just enough. Creation slowed, and the primordial dance partners, matter and antimatter, were now far more likely to find each other than to emerge anew. And when they met, they obeyed the law they were born with: total cancellation. A proton meets an antiproton, gone. A quark meets an antiquark, gone. An electron finds its perfect opposite, the positron, gone. Not even ashes remain, just energy, photons, a flash of light, and then nothing. We can't witness this moment directly. It happened billions of years ago, in a time before light could move freely through the cosmos. But its fingerprint is everywhere. The universe today is soaked in the background radiation of that annihilation, a soft hum, a thermal echo. The cosmic microwave background is not just the residue of creation, it's also the funeral pyre of symmetry, the afterglow of destruction on a universal scale. And yet, something survived. This is where the story becomes strange, because the math, again, demands nothing remain. Equal amounts in, equal amounts out. A cosmic equation with zero as the solution. But the universe cheated. It left a remainder. For every 1 billion annihilation events, one particle of matter had no partner. Just one, unmatched, ungreeted, left standing on a battlefield littered with mutual erasure. These lone particles didn't know it yet, but they had inherited the cosmos. They were the winners of the unlikeliest lottery, not by force or design or merit, simply by being the ones left over. It is perhaps the most profound understatement in physics. We owe our existence to a tiny asymmetry in the early universe, a 1 in a billion statistical blip. Had the numbers aligned just slightly differently, one fewer unbalanced proton, one fewer lonely electron, there would be no stars, no chemistry, no biology, no thought, no you. Just a universe of light, an empty radiation bath expanding forever into nothingness. But instead, we got this. We got galaxies, nebulae, black holes, Beethoven, bacteria, love, language, mathematics, metal, regret, wonder. All of it balanced on a subatomic miracle, and yet that miracle is unexplained. We call it baryon asymmetry, but that name is simply a label for a question, one of the deepest questions we can ask. Why didn't matter and antimatter exist in perfect balance? Why did the universe prefer one over the other? There are theories, dozens, but no proof. Some suggest a field, like the Higgs, but older, stranger, may have favored matter in those first femtoseconds. Others invoke leptogenesis, where neutrinos, the most elusive of particles, decayed in ways that subtly unbalance the scales. Still others speak of CP violation, a fundamental preference for left over right, forward over back, positive over negative. In a universe that should be indifferent, something chose a side. It's worth pausing here. Think of how delicate this imbalance must have been. 1 part in a billion. That's a deviation smaller than almost anything we encounter in nature, a fingerprint in a hurricane, a whisper in a volcano. And yet it was enough to birth reality. This is not simply a curiosity, it is a clue, perhaps the most important clue, to what lies beyond the physics we know. Because if we could understand the mechanism behind the imbalance, we might discover entirely new laws, hidden symmetries, broken rules, a deeper architecture beneath the known. It could explain not only why we exist, but whether we had to. Because if the imbalance was inevitable, then maybe life was too. Maybe it was always going to end this way, with sentient beings staring back at the void, wondering why they're here. But if the imbalance was random, then existence itself is a cosmic accident. An accident we are only just beginning to grasp. What's equally strange is this. Antimatter didn't disappear. It was destroyed, yes, but only in the sense that it annihilated with its mirror. And in doing so, it transformed into something else. Energy. The energy released in the Great Annihilation wasn't wasted. It flooded the early universe, contributing to the vast reservoir of photons that still permeates all of space. Those lonely gamma rays became part of the thermal budget of the cosmos. They shaped its expansion, its temperature, its fate. In a way, the death of antimatter was not the end, but a transformation. And perhaps, like all good stories, it left behind a trace of itself. Today, we still find antimatter in the radioactive decay of certain elements, in cosmic rays, in lightning storms, and deep within the collisions inside particle accelerators. Antimatter, it seems, can be coaxed back into the world, briefly. Glimpses of the twin that once stood beside us at the dawn of time. But only briefly, because when we create antimatter today, it still follows the rules of its birth. It still seeks its partner. And when it finds one, it vanishes. There's no negotiation, no delay. The reaction is instant, total, as if the universe itself remembers what it once tried to erase. You might wonder, what would happen if we found antimatter in large quantities today? Could we trap it, store it, use it? Theoretically, yes, but the risks are enormous. Even a few nanograms of antimatter would obliterate everything in its vicinity if containment failed. It's not just dangerous, it's perfectly dangerous. And yet, the potential is staggering. We'll explore that soon. But first, we must dive deeper into how we've tried to recreate the past, to observe the broken symmetry directly. Because buried within our most sophisticated machines, in the tunnels beneath Switzerland and the vacuum chambers of Japan, lies humanity's best attempt to unlock the secrets of the Great Annihilation. We've watched it happen in miniature, but the original moment remains hidden. And maybe, just maybe, the universe prefers it that way. There's something deeply unsettling about survival. It implies something was meant to be lost. After the Great Annihilation, when nearly all the matter and antimatter in the universe destroyed each other, a fragile sliver of reality was left behind. Matter, unpartnered, unmatched, inexplicably spared. These are the survivors, the 1 in a billion particles that made it through the primordial culling. We are made of those survivors, but no one knows why they survived. We give it a name. Baryogenesis, the process that produced more baryons, like protons and neutrons, than antibaryons in the early universe. But this is not an answer. It's a question dressed in a lab coat. It tells us only that something tipped the balance, that in the first seconds of time, the universe committed a crime against symmetry. Matter and antimatter were supposed to cancel each other perfectly. They didn't. Something cheated. And now, billions of years later, we're still looking for the fingerprints. What we know is this. In the microseconds after the Big Bang, as temperatures dropped and the cosmic furnace cooled, interactions between particles became less frequent and less energetic. The balance between matter and antimatter began to favor annihilation, a race toward zero. But instead of a dead universe of pure light, something changed the odds. Somehow the scales tipped just enough to leave a residual fraction of matter. That residual became everything. To understand how this could happen, we need to understand the rules and how they might be broken. In 1967, a Russian physicist named Andrei Sakharov proposed 3 conditions that must be met for baryogenesis to occur. 3 cosmic loopholes that would allow the universe to prefer matter over antimatter. 1. Baryon number violation. There must be processes that allow the number of baryons to change. In simple terms, physics must allow the universe to create more matter than antimatter, breaking one of its own sacred rules. 2. C and CP violation. The laws of physics must behave differently for particles and antiparticles, C violation, and must not be perfectly symmetric under the combination of charge and parity, CP violation. If matter and antimatter behave exactly the same, there's no reason for one to win. 3. Departure from thermal equilibrium. The universe must be out of balance. Symmetry breaking requires the cosmos to be in a state of change, not static, not in equilibrium. The early universe, expanding and cooling rapidly, qualifies. These three ingredients, violation, asymmetry, disequilibrium, might have been present in the first instance of time. But here's the problem. We've only observed small traces of these effects in the laboratory. The standard model of particle physics, our most successful scientific framework, does predict CP violation. We've seen it in kaons and B-mesons, particles that decay ever so slightly differently than their antiparticle counterparts. It's real, it's measurable, but it's not enough, not by a long shot. The CP violation observed in experiments is too weak to account for the vast imbalance we see in the cosmos today. It's as if nature handed us a matchstick and asked us to explain a wildfire.
Which leads us to a painful conclusion. The answer must lie beyond the standard model.
Some physicists have turned to supersymmetry, a theoretical extension that posits every particle has a more massive superpartner. These particles could contain new forms of CP violation, buried beneath layers of mass and energy we've yet to access. Others propose leptogenesis, a cousin of baryogenesis, in which the imbalance begins not with baryons but with leptons, like the elusive neutrino. In certain theories, heavy right-handed neutrinos, particles not yet discovered, could have decayed in the early universe in a way that favored matter. Their decay patterns, if asymmetric, could have cascaded into the baryonic realm. There are even ideas involving time reversal symmetry, suggesting that the early universe may have had a temporal direction, a bias, that favored creation over cancellation. In a cosmos where time flows asymmetrically, could matter and antimatter have been drawn to different fates? These are not idle speculations. They're driving billion-dollar experiments, massive underground detectors, particle accelerators slamming ions together at near-light speed. We're trying with all our technology to recreate the conditions of the earliest universe, to see if we can provoke imbalance again. And yet, it eludes us. Every measurement, every collision, every trace of antimatter we capture and examine behaves almost exactly like its matter counterpart. Mass, spin, energy, mirrored to perfection. Almost, but not quite. Somewhere in the tiniest decimal places, some physicists believe, is the fracture line, the crack in the cosmic mirror that let matter escape. It's not just an abstract mystery, it's existential. Because if we understood what caused baryogenesis, we wouldn't just know why we're here. We'd know whether other universes, other timelines, could exist without it. Universes that annihilated themselves into light. Universes that never ask questions, because they never had observers. We live in a universe where something happened that wasn't supposed to. And because of that, we exist. That's not just a mystery, it's a gift. But it's also a warning. Because whatever tipped the scale in favor of matter, whatever shattered that perfect balance, did so with frightening precision. 1 part in a billion, a tilt so subtle it could vanish with a slight change in physics, a different Higgs mass, a slight shift in inflation, a quirk in the quantum foam. This raises an uncomfortable question. Was our existence an accident, or was it inevitable? If the answer lies in the laws of physics, if there's a fundamental asymmetry baked into the very fabric of reality, then perhaps life was always destined to emerge. But if it was random, if the imbalance was a dice roll that happened to land in our favor, then the universe is indifferent. And we are lucky, but not necessary. That's the difference between meaning and chance. And as we look deeper into the past, searching for answers in decaying particles and elusive neutrinos, we may have to confront something even stranger. What if we can't know? What if the very act of survival obscures the reason for it? Still, we look. Because somewhere in the ashes of annihilation, a secret waits to be uncovered. And it's written in the language of symmetry betrayed. There are places on Earth where humans have recreated the first moments of the universe. Not in myth, not in metaphor, but in stainless steel chambers, buried deep beneath the surface. in rings of superconducting magnets that stretch for kilometers, in vacuums so pristine they rival the emptiness of space. This is where we hunt ghosts, the ghosts of symmetry, the ones we never knew but who died so we could live. This is where we conjure antimatter. It begins, as it always does, with energy, immense energy, focused, accelerated and weaponized, not to destroy but to reveal. When particles are smashed together at near the speed of light, the violence of that collision briefly tears a hole in the fabric of the familiar, and from that wound the past leaks in. At facilities like CERN, home to the Large Hadron Collider, protons are spun through a 27-kilometer loop beneath the border of France and Switzerland. They travel so fast their mass increases, their time slows, and then they collide. In that moment, temperature and density soar to unimaginable levels. For a fraction of a second, the conditions mimic those of the early universe, a trillionth of a second after the Big Bang. And from the wreckage, antimatter is born. Tiny bursts, fleeting, a positron here, an antiproton there. Particles that do not belong in this world, particles that by all accounts were meant to vanish 13.8 billion years ago. But there they are, real, measurable, and terrifyingly fragile. Creating antimatter is not the problem. We do it all the time, in colliders, in certain radioactive decays, even in the upper atmosphere where cosmic rays strike the Earth. No, the problem is keeping it. Because antimatter, when it encounters matter, annihilates instantly. And we live in a world made entirely of matter. Every atom in the air, every molecule in the walls, even the instruments used to detect antimatter are made of the very thing it cannot touch. So we had to build a prison. At CERN, that prison is called the antiproton decelerator, a machine designed not to smash particles together, but to slow antimatter down, to tame it, to hold it. Imagine trying to bottle lightning inside soap bubbles. That's roughly the scale of the challenge. To store antimatter, scientists use magnetic traps, devices that suspend charged particles in mid-air using overlapping magnetic fields. The antimatter floats, never touching the walls. If it drifts even slightly, if the fields wobble or the vacuum degrades, annihilation is immediate. A flash, a gamma ray, a warning. In 2011, the Alpha experiment at CERN managed to trap anti-hydrogen, an antiproton and a positron for a full 1,000 seconds. It was a milestone, proof that antimatter could be held, studied, maybe even used. But the quantity, just a few dozen atoms, enough to light a pixel. And yet the implications are vast, because in those fleeting moments, scientists were able to examine the behavior of antimatter, to compare it meticulously to its matter counterpart. Do they fall at the same rate in gravity? Do they respond identically to light? Do they obey the same symmetries? So far, yes, but that's the problem. Every test, every collision, every measurement has shown us a haunting truth. Antimatter behaves almost exactly like matter. Almost.
It's in the almost that the truth might hide.
Because we are not looking for gross differences. We are looking for the tiniest crack, the ghost of the asymmetry that let us exist. A particle that wobbles when its mirror does not. A decay that favors the left when it should be right. A clue that something, somewhere, long ago, broke the rules. That's what keeps these colliders running. Not just curiosity, but hope. The hope that if we push hard enough, we'll see through the veil. That beneath the perfect symmetry of equations, there's a fingerprint left by the universe's original crime. But there's something else driving us too. Fear. Because the more we study antimatter, the more we realize how unnatural our world is. We're not the default, we're not the standard. We're the remainder, a scar on the face of symmetry. And scars raise questions. Could there have been a universe where antimatter won? Where matter was wiped out and the cosmos formed around the opposite charge? A mirror universe, indistinguishable in physics, but inverted in every atom. If so, it might still exist. Somewhere, drifting in the cold, far-flung corners of space, an antimatter galaxy might be spinning, its stars burning with anti-hydrogen, its planets built from anti-oxygen and anti-carbon, a place where, if you set foot upon it, you would vanish, atom by atom, in a bloom of light, and yet it would feel no different. That's the haunting beauty of antimatter. It's not evil, it's not alien, it's identical until it isn't. And the boundary between our world and that one is less than the width of a proton. That's why we search. That's why we build our colliders deeper, colder, quieter. Because if we can isolate the rules that govern antimatter, we may be able to trace the path backward, to the moment the symmetry broke, to the tipping point, to the choice the universe made, or failed to make. And in that knowledge we may glimpse something more profound than physics, a reason. But for now we keep the ghosts in their cages, floating, suspended, silent, watching us with no eyes, waiting. We don't know what they remember. We don't know if they remember anything at all. But we do know this. They come from a world that should have been. A mirror world, shattered in silence. A twin, erased before it had the chance to reflect. And sometimes, when the detectors blink and the readings spike, we feel it. Not fear, recognition. We measure wealth in many ways: gold, land, power, energy. But there is one substance so valuable, so volatile, and so impossibly rare that its worth defies economics: antimatter. Not in science fiction, not in theory, in reality, tangible, quantifiable, and almost completely untouchable. A single gram, just 1 gram of antimatter, if it could be isolated, stored, and annihilated with an equal amount of matter, would release roughly 90 terajoules of energy. That's twice the yield of the atomic bomb dropped on Hiroshima, from something the weight of a paperclip. This is not a fantasy. It's not theoretical. It's E equals mc squared in its most terrifyingly pure form. When matter meets antimatter, their entire mass is converted into energy. No ash, no radiation waste, just annihilation, total and perfect. And yet we don't use it, not because we don't want to, but because we can't afford it. Antimatter is the most expensive material ever produced by humans. Estimates vary, but conservative figures place the cost of creating 1 milligram of positrons, the antimatter equivalent of electrons, at over $25 million. Scale that up to 1 full gram, and you're looking at $25 billion. And that's just to make it. Storing it? That's another issue entirely, because antimatter doesn't just sit on a shelf. It can't be poured into a container or sealed in a vial. The moment it touches ordinary matter, the walls of a container, the air around it, the atoms of your hand, it vanishes in a flash of gamma radiation. So to keep it, we levitate it. Using penning traps, magnetic bottles, and ultra-high vacuum chambers, scientists can suspend antimatter in empty space, isolated from everything, including itself. If 2 particles of antimatter touch each other, they're fine. But if either one touches matter, the result is instant. Even the smallest contact releases photons with energies in the range of 511 kilo-electron volts, gamma rays capable of penetrating through bone, flesh, and metal. It's not just destructive, it's cleanly destructive. Antimatter doesn't explode, it erases. This is what makes it so alluring and so feared, because the energy potential of antimatter is not matched by any other fuel, not nuclear fission, not hydrogen bombs, not even the most exotic proposals for fusion. In theory, a single kilogram of antimatter, if such a thing could ever exist, would release energy equivalent to 43 megatons of TNT. That's nearly 3 times the yield of the Tsar Bomba, the most powerful weapon ever detonated on Earth. Now imagine that energy, not unleashed in chaos, but harnessed perfectly. Antimatter is the ultimate rocket fuel. In propulsion models drawn up by NASA and other agencies, an antimatter-powered spacecraft could reach a significant fraction of the speed of light. The only thing holding us back is reality. At current production rates, it would take billions of years to create enough antimatter to propel a single human out of the solar system. And even if we had it, storing it safely would require technological revolutions we haven't begun to achieve. Still, the idea persists, because antimatter is not just energy, it's pure energy. No moving parts, no exhaust, no residual mass, just conversion, clean, elegant, devastating. There are rumors, whispers really, that military agencies have taken interest. That miniature antimatter devices could, in theory, serve as trigger mechanisms for thermonuclear weapons, replacing conventional fission detonators with something much smaller, much faster, much cleaner. It's hard to verify these claims, but the interest is logical. After all, if you could control antimatter, truly control it, you would hold the most powerful force ever wielded by any civilization, anywhere. And yet, we don't. Not because we're wise, but because we're incapable. In all of human history, we have produced less than a nanogram of antimatter. That's 1/1000th of a gram, and even that we could barely hold for more than a few seconds. It's like building the world's most powerful dynamite and realizing your hands are made of matches. Still, the dream lingers. The European Organization for Nuclear Research, CERN, continues to lead efforts in producing and studying antimatter. Other facilities like Fermilab in the US and J-Park in Japan contribute to the global effort, but no one is scaling it. No one has found a way to make antimatter practical, and yet its value persists, not in dollars, but in potential. Because antimatter forces us to rethink what energy is. It challenges us to imagine a future where propulsion doesn't come from combustion, or fission, or even fusion, but from erasure. The annihilation of opposites. Some envision interstellar arcs, powered by antimatter engines, capable of reaching Alpha Centauri in decades instead of centuries. Others see medical breakthroughs, antimatter beams that target cancer cells with unprecedented precision, leaving healthy tissue untouched. All of it real, all of it unreachable. And there is a darker side to the dream. Because the weaponization of antimatter isn't fiction, it's just logistics. If a nation or a rogue actor ever solved the storage problem, even partially, the consequences could be apocalyptic. Antimatter doesn't need warheads, it doesn't need uranium, it needs only contact. There are no treaties banning antimatter weapons, because there's no need, for now. But that window may not last forever. And so we find ourselves in a strange position. We've glimpsed the most potent form of energy in the universe, the force that shaped the early cosmos, that powered annihilation, that left behind the flickering embers we now call matter. We've recreated it, measured it, held it for seconds at a time, but we cannot use it, not yet. Perhaps that's a mercy. Perhaps the universe is not just fragile, but wise. It gave us the spark, but placed it just beyond our reach. A challenge, a warning, a gift we are not yet ready to unwrap, but we will try, because we are children of imbalance, descendants of a tilted scale, survivors of a war we never fought, and the fire that forged us still flickers in our hands. What if everything we know has a twin? Not just a metaphorical twin, not a reflection in a pond or an echo down a corridor, but a true counterpart. Identical in structure, opposite in charge, as vast as our cosmos, as old as time itself, and utterly incompatible with our own. What if there is an antimatter universe hiding in plain sight? For decades, physicists have entertained a question so radical it tiptoes the line between science and science fiction. Could some galaxies, or even entire regions of the universe, be composed not of matter but of antimatter? The idea seems absurd, implausible, and yet, disturbingly, it remains possible. Let's start with what we know. When we observe distant galaxies, we're not seeing atoms directly. We're seeing light, photons emitted or reflected by matter. But photons don't care whether they came from matter or antimatter. An anti-electron falling from an excited state in an anti-atom emits the exact same kind of photon as an electron does in ordinary matter. There is, at the observational level, no difference in the light they produce. So when we look into the sky, scanning billions of light years in all directions, we're making a silent assumption that the structures we see are made of the same stuff we are. But we don't know that, because light can lie, and antimatter is nothing if not deceptive. But surely, you might think, if there were galaxies made of antimatter, we would see signs, some cosmic warning, some frontier where the two worlds touch and burst into annihilation. That's the catch. If matter and antimatter galaxies were mingling freely, the boundaries where they meet would be catastrophic. Intergalactic collisions, or even gentle mingling of gases between a matter and antimatter galaxy, would result in immense gamma-ray bursts, high-energy radiation screaming across the universe. And yet, we don't see that. The universe is suspiciously quiet. Too quiet. That silence has long been taken as evidence that antimatter galaxies probably don't exist. But probably is not certainty. What if the distribution of matter and antimatter is not random? What if they were segregated, divided at birth like oil and water in a cosmic centrifuge? Imagine for a moment that the early universe contained domains, patches where matter dominated and others where antimatter took hold. If the distances between these regions were vast enough and expansion fast enough, they could have remained permanently isolated, a patchwork cosmos, a quilt of contradiction. In such a model, we could be living in a matter-dominated sector, surrounded by antimatter realms so distant that even their collisions are rare or buffered by enormous voids. The borders are there. We just haven't seen them. But there are stranger possibilities still. Some researchers have proposed the existence of anti-stars, stars made entirely of antimatter, indistinguishable in their light, but subtly different in their nuclear makeup. They would fuse anti-hydrogen into anti-helium, shine, burn, die, just like any star we know. Recently, telescopes scanning the cosmos have detected anti-helium nuclei among cosmic rays, a rare exotic signal that shouldn't exist in our matter-dominated universe. It might be an anomaly, a fluke of cosmic ray collisions, or it might be evidence. Evidence that somewhere out there, in a region untouched by our matter, an anti-star is dying. Its remnants drifting toward us, silently whispering, "I am real." There are even experimental searches underway. Instruments like the Alpha Magnetic Spectrometer, mounted on the International Space Station, are actively hunting for heavy anti-nuclei, anti-carbon, anti-oxygen, particles that could not have been formed in collisions, but only in antimatter stars. If they're found, the game changes, because then the mirror is real. A cosmic twin, built from the same rules, powered by the same physics, but reversed in every atom. Of course, the question follows, why didn't we annihilate? If antimatter galaxies exist, why hasn't our own galaxy collided with one? Why is our corner of the universe so suspiciously calm? The answer may lie in inflation, the theory that the early universe expanded faster than the speed of light, stretching quantum fluctuations into vast cosmic structures. Inflation could have pushed matter and antimatter regions so far apart, so quickly, that they never had time to mix. By the time matter knew that antimatter existed, it was already too late to touch it. And so, the mirror was sealed, locked behind the accelerating expansion of space. But let's imagine the unthinkable. What if we found one, a galaxy, perhaps billions of light years away, made of antimatter? What could we do? We couldn't visit it, we couldn't send a probe, not without catastrophic consequences, because our ships, our sensors, our very atoms would ignite upon contact. Not with heat, with symmetry. The moment matter touched antimatter, they would cancel one another out. A slow collision would be no safer than a fast one. It is not speed that matters, it is presence. Our explorers would burn like kindling in the presence of its air. And yet, it would be familiar, so heartbreakingly familiar. Its stars would shine the same, its physics would work the same, its laws, its structures, even its chemistry, nearly identical. But the moment of contact would be annihilation, a mirror that cannot be touched. It raises a final, chilling possibility. What if life evolved there? What if, on a distant antimatter world, intelligent beings look up at the stars and wonder the same things we do? What if they, too, built colliders, searching for clues about the imbalance that erased our kind from their half of the cosmos? What if we are their ghosts? Two civilizations, born of the same laws, separated by charge, united only by mystery. And if we ever meet, it will be the last thing either of us does. There are absences in nature that feel loud. The dog that doesn't bark, the phone that doesn't ring, the darkness that lingers longer than it should. In cosmology, silence isn't just the absence of sound, it's the absence of events, things that should be happening, but aren't, signals that should scream through space and instead are missing. And nowhere is this silence more haunting than in the search for antimatter galaxies. Because if antimatter exists, truly exists, on a cosmic scale, then the universe should be a symphony of destruction. Not theoretical destruction, observable destruction. Galaxies made of matter and antimatter should eventually collide, or drift close enough for gases to mingle. When that happens, their edges would erupt in chaos. Interstellar hydrogen meeting anti-hydrogen, molecular clouds brushing against their inverted twins. The result would be unmistakable: gamma-ray bursts, flashes of high-energy radiation born from mutual annihilation on a grand scale, not once, not rarely, constantly. And yet, the sky is quiet, not empty, not silent in the literal sense. Space hums with the whisper of radio waves, the glow of microwave background radiation, the shimmer of starlight. But in all that noise, we do not hear what we most expect. We do not hear the scream of symmetry breaking. The gamma-ray signature of matter-antimatter annihilation is well known. It's precise. 2 photons, each with an energy of 511 kilo-electron-volts, emitted back-to-back, a perfect calling card of electron-positron destruction. We can detect it in labs, in PET scanners, in particle accelerators, even in rare terrestrial phenomena like lightning storms. The fingerprint is clear, and yet, when we point our instruments to the cosmos, expecting to see the cosmic equivalent of antimatter borders ablaze, we see nothing. Not nothing in the philosophical sense, but nothing where there should be something. This is not just curious, it's damning. The absence of annihilation radiation is the strongest argument against the existence of large antimatter structures in our universe. If antimatter galaxies exist, they are hiding far better than they have any right to. Some argue they're simply too far away, isolated beyond our observational horizon. Others suggest that cosmic inflation may have flung matter and antimatter regions so far apart that their borders are gone, erased by expansion. But these are speculations made in the shadow of silence. Because here's the truth: the more sensitive our instruments become, the quieter the sky gets. Satellites like Fermi, Integral, and Comptel have scanned the heavens with extraordinary precision. They detect gamma-ray bursts from neutron stars colliding, from black holes devouring matter, from distant quasars lighting up the void. But the signature of large-scale antimatter annihilation, the one we're waiting for, never arrives. Some researchers cling to anomalies, a spike here, a line there. But these signals are often local, connected to solar flares or terrestrial interference. When filtered, when modeled, when challenged, they fade, and the quiet returns. This absence forces us to confront an uncomfortable possibility. What if we're alone? Not in the biological sense, not in the search for life, but alone in matter, the sole survivors of the Great Annihilation, the only region where symmetry broke in favor of existence. A cosmic island, surrounded not by antimatter but by emptiness. The idea is isolating, and worse, it's statistically baffling. Why would the universe favor matter in one corner and not balance the scales elsewhere? Why is the sky not on fire? Perhaps the symmetry didn't just break, perhaps it shattered permanently, everywhere. Perhaps whatever tilted the balance in our favor did so universally, not locally, rewriting the rules of creation in the first femtoseconds of time. If so, then antimatter never had a chance. It wasn't a border war, it was extinction, a genocide of physics baked into the blueprint of being. But there is one other explanation, one that whispers from the edge of credibility, one we rarely voice aloud because of what it implies. What if the silence is intentional, not the result of absence but of concealment? What if antimatter regions do exist, but are structured in such a way as to avoid detection, hidden behind massive voids, isolated in the folds of space-time, using mechanisms we don't yet understand? It sounds like paranoia, like cosmological conspiracy. But then, so did inflation, so did dark energy, so did quantum entanglement. The universe again and again has revealed that our instincts are naive, that reality is not obliged to be simple, or fair, or visible. And in that shadow, the silence of the sky becomes less reassuring and more disturbing. Because silence does not mean safety. It may mean that we are missing something so vast, so fundamental, that we no longer even recognize it as missing. It may mean that we're not alone, but merely quarantined. Matter and antimatter may not be separated by space, but by structure, by rules we haven't discovered, or by choices made at a scale beyond comprehension. Or perhaps we are alone, the only region where matter won. Not chosen, not special, just fortunate. A cosmic error that slipped through the cracks, an imperfection left uncorrected, the one bubble in a quantum froth where symmetry blinked, and we mistake that blink for design. Whatever the answer is, it lies beyond this quiet, beyond the gamma-ray stillness, beyond the silence that stretches between galaxies. And perhaps one day that silence will be broken by a photon, a burst, a border breached, and then we'll know, not just that antimatter is out there, but that it's coming this way. We stare at the stars with a kind of reverence. They are the candles of our cosmic cathedral, steady, familiar, ancient. They warm our nights and map our past. But what if some of them don't belong? What if some stars are made of antimatter? It sounds absurd, implausible, like science fiction clinging to the coattails of science fact. But in recent years, what was once dismissed as impossible has quietly crept into the realm of the plausible. Because the deeper we look into the universe, the more it begins to whisper secrets. And one of those secrets is that some stars may not be like the others. Some may be anti-stars, stars made entirely of antimatter. And they might already be among us. Let's unpack the idea. In principle, there is nothing stopping an anti-star from existing. Antimatter, when isolated from matter, behaves identically. An antiproton and an anti-electron can form anti-hydrogen, just as their positive counterparts form hydrogen. That anti-hydrogen can fuse into anti-helium, releasing energy in the form of photons. Photons, crucially, do not distinguish between matter and antimatter. The light emitted from an anti-star would look exactly like that of an ordinary star. Its temperature, its color, its spectral lines, all identical, which means that in a sky of 200 billion stars, we may have already seen hundreds of anti-stars and never known it. But if that's true, a chilling implication follows. Somewhere along the way, during their formation, their movement or their death, those anti-stars must have avoided any significant interaction with the matter-dominated universe. Because a single collision with a matter-based gas cloud, asteroid, or cosmic dust field would ignite an annihilation reaction of catastrophic proportions. They would be beacons of destruction. And yet, the sky is eerily calm. So if anti-stars exist, they must be hiding, shielded, isolated in regions of space where the matter density is low, possibly born in antimatter-rich domains that never mixed with our own. Or they could be survivors, ancient relics from the early universe, remnants of a time when matter and antimatter were still vying for dominance. Perhaps these anti-stars drift in the galactic halo on wide orbits far above and below the galactic plane, like ghosts watching from the dark, and the hunt has already begun. In 2021, researchers analyzing data from the Fermi Gamma Ray Space Telescope identified a set of 14 stars emitting gamma rays at unusual energies. The signals were consistent with the kind of photon you'd expect if matter were slowly interacting with antimatter on the surface of a star. Low-level annihilation events, not explosive but persistent, not proof, but possibility. A whisper. What makes this intriguing is that these candidate anti-stars do not fit neatly into the standard categories of known gamma-ray sources. They are not pulsars, they are not black holes, they are not active galactic nuclei. They are quiet, steady, strange. Could they be stars with a secret? Theoretical models suggest that anti-stars could still form in a universe overwhelmingly dominated by matter, but only under special conditions. During the early universe, small pockets of antimatter might have become gravitationally bound, collapsing into stars before encountering significant amounts of matter. If those pockets were isolated, walled off by vast voids or expansion, they might have survived. And over time, as galaxies formed and merged, some of those anti-stars could have drifted in from the galactic outskirts, fossils from a lost antimatter epoch, now floating in an ocean that would erase them on contact. There's another piece of the puzzle. The Alpha Magnetic Spectrometer aboard the International Space Station has been scanning cosmic rays for over a decade. In that time, it has detected a few anomalous particles, most notably several anti-helium nuclei. Anti-helium is rare, incredibly rare. It can, in theory, be produced in high-energy collisions, but the odds are vanishingly low. To find even a single anti-helium nucleus among cosmic rays suggests something unusual is happening. If those particles originated in an anti-star shed during a supernova or stellar wind, they could be the first physical proof of a mirror star. The problem? Verification. Detecting antimatter in space is like catching shadows in the wind. Cosmic rays bend and blur through magnetic fields. Detection rates are tiny. And even if anti-helium is confirmed, tracing it back to its source is nearly impossible. Still, the clues mount. No single piece is definitive. But the pattern, the anomalies, the silences, the strange signals, all point to something we don't understand. And when we don't understand something in the cosmos, it usually means we're looking at something new. So what would it mean if anti-stars are real? For one, it would reshape our understanding of baryon asymmetry. If isolated pockets of antimatter survived the early universe, it would suggest that the imbalance between matter and antimatter wasn't absolute. That symmetry broke locally, not universally. It would mean that the Great Annihilation wasn't complete, and that the survivors weren't only on our side, but it would also raise practical concerns. Because anti-stars, unlike ordinary stars, are dangerous, not because they explode, but because we wouldn't know we were near one until it was too late. A spacecraft approaching an anti-star would be annihilated before it even touched the surface. The interstellar dust it carries, the gases it leaks, the material it's made from, all would trigger violent reactions the moment they encountered antimatter. A ship traveling through the galactic halo might pass an anti-star by mere astronomical inches and be erased, silently, cleanly, perfectly. Which is why the search continues, cautiously. We build better detectors, we scan the skies for the faintest signals, and we ask a question that sounds like it came from myth, but is now firmly grounded in data. What if some of the stars we see are not ours, not of our matter, not of our kind? Reflections drifting just out of reach, built from the same physics, lit by the same fusion, but destined to remain untouchable. Perhaps they burn not just with antimatter, but with loneliness. A loneliness we share. In physics, symmetry isn't just a pattern, it's a promise. A silent contract between the universe and the equations that describe it. a belief as old as science itself that nature is fair, that it does not play favorites, that the laws governing particles here and now apply equally there and then. But what happens when the universe breaks its promises? What if symmetry, the sacred symmetry, is a lie? At the center of this question lies one of the most profound and unbreakable rules in theoretical physics, CPT symmetry. C for charge, P for parity, T for time. Together, they form a trinity of transformations, a cosmic mirror we expect the universe to obey. Let's break them down. C, charge conjugation. Switch every particle for its antiparticle. Positive becomes negative, matter becomes antimatter. P, parity inversion. Flip the universe like a mirror image. Left becomes right. Spin reverses. T, time reversal. Run the clock backward. Effects become causes. Entropy unwinds. Individually, these symmetries can be broken. We've seen it. We know, for instance, that certain particles violate P symmetry. They behave differently in a mirror. We also know CP symmetry is broken in specific particle decays, meaning that nature sometimes treats matter and antimatter unequally. But CPT, the combined transformation, is supposed to be untouchable. If you flip charge, flip space, and flip time, the laws of physics are supposed to remain exactly the same. CPT symmetry is not a suggestion. It is a mathematical inevitability derived from the most basic assumptions of quantum field theory, that the universe is Lorentz invariant, meaning the laws of physics don't depend on your orientation or speed through space. So when we speak of CPT, we are speaking of something foundational, a rule not written by physicists, but discovered, carved into the bedrock of reality, which is why any violation of CPT symmetry would be catastrophic. It would imply that the framework underpinning all modern physics, quantum mechanics, relativity, the Standard Model, is incomplete or even wrong. And here's where the tension begins. Because we already know that CP symmetry is violated, certain particles, like the kaon and B meson, decay slightly differently than their antimatter counterparts. It's a tiny effect, but it's real, and it's necessary to explain the imbalance between matter and antimatter. But CP violation raises a dangerous possibility. If CP can break, what about T? Could time itself be asymmetrical? And if so, does CPT symmetry still hold? To date, no confirmed violation of CPT symmetry has ever been observed. Every experiment designed to compare particles and antiparticles, mass, charge, spin, magnetic moment, has confirmed that they are, to astonishing precision, identical in all properties except charge. But we are still searching, still testing, still pushing the decimal places further and further out, hunting for the tiniest crack in the cosmic code. Because some physicists believe CPT might not be violated but emergent, a symmetry that appears true at low energies but breaks down at the Planck scale, where gravity and quantum mechanics begin to clash. In those uncharted depths, at 10 to the negative 35th power meters, space may not be smooth. It may foam and flicker. Reality itself may jitter in and out of existence. And in such a chaos, symmetry may not be a rule, but an illusion, a coincidence. This brings us to the heart of the antimatter mystery, the baryon asymmetry of the universe. The fact that matter vastly outweighs antimatter seems to require CP violation. But the CP violation we observe is too weak. Orders of magnitude too small to account for the imbalance. Something else must be happening. Some deeper symmetry must have been broken. And CPT is the last bastion. If it fails, even subtly, it could explain everything. The matter-antimatter imbalance, the arrow of time, the creation of mass, even the fabric of causality itself. But at what cost? Because breaking CPT would be more than a revolution in physics. It would be a philosophical earthquake. It would mean the universe is not just asymmetrical, but biased. That time has a direction not because of entropy, but because of preference. that the universe does not treat left and right equally, that it does not treat past and future the same, that nature is not fair, only consistent within its own broken frame. This kind of violation would imply that the laws of physics aren't eternal, but historical, born from a specific moment, shaped by specific conditions. The cosmos, in this view, is not a fixed system running on unbreakable rules, but a self-modifying structure with scars, choices, and memory. And perhaps that memory includes the Great Annihilation. Perhaps the very laws we now study were written in the aftermath of that event, coded not for balance, but for survival, written by what was left behind, by us. Of course, we haven't yet found any definitive CPT violation. Every experiment confirms it, to 12 decimal places and beyond. But confirmation is not proof. It is only absence of contradiction. And silence, as we've learned, is not the same as truth. Still, we search. At CERN in Japan, in underground neutrino observatories and orbiting satellites, scientists are designing ever more precise tests of CPT symmetry, comparing particle lifetimes, spin orientations, decay pathways, looking for the fingerprint of betrayal. Because if we find it, if CPT symmetry fails, it will not be the end of physics. It will be its rebirth, a deeper layer, a new framework, one that explains not only how the universe works, but why it looks like this, why we exist, why we remember the past and not the future, why the stars shine but the mirror remains dark. Some suspects hide in the shadows, others are the shadows. Among the strange cast of particles that populate the quantum world, neutrinos are the most elusive, and perhaps the most important. They are almost massless. They are uncharged. They barely interact with anything. They pass through planets, stars, and bodies without leaving a trace. And yet there are trillions of them moving through you right now. Born in the heart of stars, in the aftermath of supernovae, in radioactive decay, and even the Big Bang itself, neutrinos are everywhere. They are among the most abundant particles in the universe, and the least understood. But there's something stranger still. They change. A neutrino born as one type can become another, spontaneously, mid-flight, as if rewriting its own identity. This process is called neutrino oscillation, and it shattered one of the core assumptions of particle physics when it was discovered in the late 1990s. It meant neutrinos had mass, however small, and that mass was not fixed. It meant the rules were flexible, and in that flexibility some physicists began to suspect a secret. Because neutrinos, for all their ghostliness, might hold the key to one of the greatest mysteries in science, why our universe exists at all. To understand why, we need to return to the imbalance, the 1 in a billion matter surplus that survived the Great Annihilation. As we've seen, the CP violation observed in ordinary particles is too weak to explain this imbalance. But what if neutrinos play by different rules? What if their oscillations, their ability to change flavors, mask a deeper asymmetry? What if, in their earliest forms, they violated symmetry not subtly, but profoundly? This is the heart of a theory known as leptogenesis. In this framework, the early universe contained not just the 3 known flavors of neutrinos, electron, muon, and tau, but also a 4th kind, the right-handed neutrino. These particles are not part of the standard model. They are hypothetical, heavy, silent, and possibly responsible for everything. In the primordial fire of creation, these heavy right-handed neutrinos may have decayed preferentially, producing more leptons than antileptons, breaking CP symmetry in a way the known particles cannot. That imbalance could have then been transferred through complex interactions into the baryon sector, creating the matter-antimatter asymmetry we now observe. In short, neutrinos may have tipped the scale. They may be the agents of cosmic bias, the reason that matter won and antimatter lost. But the story doesn't end there, because neutrinos don't just shift identities. They also defy classification. Most particles in the universe are Dirac particles, meaning they have distinct antiparticles. An electron has a positron, a quark has an antiquark. Their opposite exists, and together they form a mirrored pair. But neutrinos might be different. They might be Majorana particles, meaning a neutrino is its own antiparticle. This idea, if true, is staggering. It would mean that in the strange quantum world, the boundary between matter and antimatter is not fixed, but blurred. That some particles do not merely mirror each other, they are each other. And if neutrinos are Majorana particles, it would offer a new pathway for neutrinoless double beta decay, a rare process that, if observed, would prove the matter-antimatter line can be crossed. We haven't seen it yet, but the search is on. Deep underground, in caverns shielded from cosmic rays, detectors the size of buildings sit in perfect stillness, waiting for a signal, a tiny flash, a whisper of decay, a betrayal of symmetry so rare it may occur only once every quintillion years per atom. But if it's real, it changes everything. It confirms that the universe remembers, that it contains particles which once chose sides, and still carry that choice. And in that choice, perhaps, lies our origin. Neutrinos also have one other trick, one that defies intuition. They interfere with themselves. A neutrino can exist in a superposition of flavors, not electron, not muon, not tau, but all three at once. As it travels, this wave function evolves, interferes, and collapses. It's as though the particle does not simply move through space. It performs a calculation about who it wants to be. This quantum ambiguity adds to their mystery and their potential. Because if something this strange played a role in shaping the early universe, then perhaps the universe itself is stranger than we imagined. And perhaps the path to understanding baryogenesis, the matter-antimatter mystery, runs not through the quark sector or the Higgs field, but through the ghosts that pass through us every second. They are invisible, but not absent. They are silent, but not inert. They do not linger, but they do not forget. There's one last possibility, one that is almost too strange to voice. Some researchers have speculated that neutrinos may not be of this universe at all, that their behavior, so disconnected from other particles, suggests a connection to hidden dimensions, or a mirror sector of physics we cannot yet detect. In this view, neutrinos are messengers, bleeding into our reality from a larger one, whispering in flavors, hinting at choices we didn't make, carrying the scars of symmetry broken before the first atom ever formed. We don't know, but we are watching. In labs carved into mountains, in detectors buried in Antarctic ice, in beams shot through hundreds of kilometers of rock, we are chasing the most elusive particle in the cosmos. Because somewhere in the flicker of a neutrino changing flavor, somewhere in a decay that doesn't produce its twin, somewhere in a silence we haven't yet heard, is the answer to why we are here, and why everything else is not. There is a pattern written into our history. We discover something beautiful, and we weaponize it. Fire became war, metal became swords, splitting the atom became mushroom clouds, and somewhere between genius and fear, between discovery and destruction, humanity learned to reach for power, not to hold it, but to wield it. And that's why, in the shadows of the Cold War, a strange question was quietly asked in secretive rooms. Can antimatter be used as a weapon? The answer was, and still is, yes. And for a time, the world's most powerful nations pursued it. Not publicly, not loudly, but persistently. Because antimatter is not just energy, it's perfect energy. No chain reaction, no waste, no half-life. When antimatter meets matter, 100% of their mass becomes energy. It's the ultimate reaction, clean, total, immediate. To military planners in the 1950s and 60s, it looked like alchemy. The idea of an antimatter-triggered bomb was born in that era, not as a fantasy, but as a classified thought experiment. If a small amount of antimatter could be produced and stored safely, it could, in theory, serve as a fuse to ignite a larger thermonuclear device. And you see, hydrogen bombs, fusion weapons, require a tremendous initial burst of heat and pressure to initiate the fusion of hydrogen isotopes. Normally, this is done using a fission-based primary stage, a mini-atomic bomb. But antimatter could do it cleaner. A few micrograms of positrons or antiprotons injected into the fusion core would annihilate with electrons or protons and release a precise, immediate pulse of gamma radiation, enough to initiate fusion directly. No radioactive trigger, no uranium, just annihilation. A theoretical pure fusion bomb with none of the long-lasting fallout. For generals dreaming of battlefield weapons that didn't irradiate civilians or leave trails of nuclear ash, this was the holy grail. And so, deep within US national labs, Lawrence Livermore, Los Alamos, classified projects explored the idea. Declassified documents from the late 1980s reveal explicit discussions of antimatter as a trigger mechanism, as a beam weapon, even as a way to ignite thermonuclear fuel in space. In one report from 1986, researchers outlined the possibility of building antimatter-based propulsion and weapon systems by the early 2000s, if only antimatter could be produced in sufficient quantities. But there it was again, the obstacle. Cost, containment, control. At the time, and even now, creating antimatter is astronomically expensive. Producing even a nanogram requires particle accelerators operating at massive energy inputs, and the process is wildly inefficient. For every antiproton captured, trillions of others are lost. And storage, a nightmare. Antimatter cannot touch anything, not even the walls of its own container. It must be suspended in electromagnetic traps, held in perfect vacuums, cooled to near absolute zero. And even then, it doesn't last. Stray fields, vibration, a microscopic imperfection, and the result is detonation. Still, the fascination lingered. The Soviets explored it too. Though less is known about their programs, documents from the post-Soviet era suggest they were aware of the possibilities and the same limitations. Some reports hinted at speculative proposals involving space-based annihilation beams aimed not at cities but at missiles, to disable them with pure energy bursts before they could strike. Then came the Strategic Defense Initiative, the US Star Wars program, proposed under President Reagan. Some designs included antimatter-based directed energy weapons, hypothetical devices that could convert tiny amounts of antimatter into concentrated particle beams capable of disabling incoming ICBMs from orbit. Nothing came of it, at least, nothing we were told. Because the problem never changed. We could theorize antimatter bombs, we could sketch them, simulate them, but we could not build them. Not in a way that was stable, repeatable, or survivable. And perhaps that was a mercy. Because while a conventional nuclear bomb leaves behind devastation, fire, radiation, fallout, an antimatter device leaves behind nothing. No fragments, no residue, no radioactive signature, just a flash of light, a release of energy, a vaporization. It is the perfect crime against matter itself. There's a darker thought here, one that lingers. Imagine a world where the containment problem is solved, where antimatter is created in small but usable quantities, not grams but micrograms, enough to trigger controlled fusion, enough to erase a square block, enough to destroy a bunker silently, cleanly, without warning. What kind of weapon would that be? Not a deterrent like traditional nuclear arms, but a tool, precise, untraceable, usable. And that's what terrified some defense analysts. Antimatter weapons wouldn't start a world war. They might end one before it begins, or be used to erase key infrastructure, or to assassinate, destabilize, coerce. They would be weapons for the shadows, which is why international treaties and the Comprehensive Nuclear Test Ban Treaty, the Non-Proliferation Treaty, don't even mention antimatter, because no one has built one. But if they did, there would be no warning, no mushroom cloud, just silence. Of course, some scientists still dream of antimatter for peaceful purposes, as propulsion, as energy, as medicine. But the line between innovation and weaponization is razor thin. We should know, we crossed it with fission, with fusion, with drones, with AI. Antimatter is no different. It is the most powerful substance ever conceived. It offers a universe of potential and a universe of risk. And in our long history of curiosity colliding with conflict, it's easy to see where that path leads. So perhaps it's fortunate we cannot make more. Perhaps in its rarity, antimatter remains what it always was, a warning. Not just of what the universe can do, but of what we might. In space, there is no friction, no road, no air, no sound, just vast emptiness, and the haunting inertia of motion unopposed. To move through it, truly move, requires more than fuel. It requires force, precision, and power. It requires something close to impossible. And yet for decades, physicists and engineers have dared to dream of a propulsion system not built from fire or fuel, but from annihilation. Because in all the known universe, there is no energy source more potent than the meeting of matter and antimatter. A reaction that converts 100% of mass into pure energy, no waste, no residue, just light, just momentum, just fire from nothing. It is, on paper, the ultimate engine. And if we could harness it, truly harness it, we could go farther and faster than any rocket ever built. Not to the moon, not to Mars, but to the stars. Let's step back. Current chemical rockets, like the ones that launch our satellites and space probes, operate with an efficiency ceiling. Even the mighty Saturn V, which carried humans to the moon, converted only a tiny fraction of its mass into thrust. The rest, burned, lost, left behind. Fusion offers more, with mass-to-energy conversions around 0.7%. It's cleaner, more efficient, and still beyond our reach for propulsion. But antimatter converts 100%. When an antiproton meets a proton, or a positron meets an electron, they annihilate, not destructively, but perfectly. Their entire mass becomes energy in the form of gamma rays, neutrinos, and kinetic release. It is the closest thing physics allows to alchemy, and this, for propulsion engineers, is not just impressive, it's revolutionary. A spacecraft powered by antimatter could, in theory, achieve velocities approaching 10% the speed of light. That's fast enough to reach Alpha Centauri, our nearest stellar neighbor, in under half a century, and with more advanced configurations, perhaps more. But theory is a gentle landscape. Reality is less forgiving. Because while antimatter propulsion has been modeled, simulated, and studied extensively, from NASA's Firefly concept to antimatter-catalyzed fusion drives, the same three words always return: production, containment, control. Let's start with production. Creating antimatter requires enormous energy input. At present, the world's most advanced facilities, like CERN, can produce about 1 to 10 nanograms of positrons per year, and that's under ideal conditions. To power even a paperclip-sized spacecraft using antimatter would require milligrams, at minimum. To drive a crewed mission beyond our solar system, grams. We're not just short, we're galaxies short. Next comes containment. As we've explored before, antimatter cannot touch matter, not even slightly, so any propulsion system must store it in magnetic traps, in perfect vacuum, likely at near zero temperatures. Then it must release it, carefully in pulses directed, without catastrophic leakage. This is not engineering, it is balancing thunder on a needle, and yet, researchers persist. At Penn State, NASA's Institute for Advanced Concepts, and other theoretical labs, scientists have proposed elegant systems. One involves antiproton-catalyzed microfusion. In this model, tiny doses of antimatter are injected into pellets of deuterium-tritium fuel. The annihilation provides just enough heat to ignite a mini-fusion reaction, which then propels the ship forward, like a nuclear pulse drive, but without fission. Another concept is the beamed core engine, where charged pions produced from matter-antimatter annihilation are funneled through a magnetic nozzle, creating direct thrust. The result? High efficiency, no chemical combustion, just pure momentum from mass converted into motion. The performance numbers are astonishing. Simulations suggest specific impulses, a measure of propulsion efficiency, hundreds of times greater than chemical rockets. In a vacuum, such a drive could accelerate continuously, reaching fractions of light speed over months or years. In other words, true interstellar capability. But there are caveats, always the caveats. Gamma rays, a byproduct of annihilation, are incredibly difficult to shield against. A functioning antimatter engine would have to manage enormous radiation, requiring shielding heavy enough to offset its propulsion gains. Then there's safety. A containment failure wouldn't cause a slow leak or a sputter. It would result in instant annihilation, a release of energy that could vaporize the spacecraft and sterilize anything nearby. Even the storage tanks themselves, if improperly constructed or exposed to vibration, could become bombs. The stakes are high. The consequences are unforgiving. Still, we dream. Because in the darkness between stars, there is no room for hesitation. Chemical rockets are useless. Solar sails fade in the void. Even fusion engines, majestic as they may be, are slow. But antimatter, if mastered, is the one key that could unlock the galaxy. It's also a quiet one, because unlike fusion or fission, antimatter doesn't require massive facilities. It doesn't need plutonium or uranium. Once the technology matures, a gram of antimatter could sit in your palm. Invisible, humming with annihilation, waiting. It's not just a power source, it's a promise of ships that don't just orbit but leave, of probes that don't just fly but arrive, of missions not measured in years but in lifetimes. Generational voyages through the deep black with antimatter guiding the way. It's poetic, dangerous, inevitable, and perhaps someday the first true starship will ignite not with fire, but with symmetry. Two particles, one matter, one antimatter, touching, erasing, and from their vanishing, a thrust forward into the dark. We began this journey with a question so simple it feels like a child's, and yet so profound it still haunts the minds of physicists. Why does anything exist at all? In the cold arithmetic of the Big Bang, the answer should have been nothing. Matter and antimatter, born in equal measure, should have cancelled each other out. A flash, a fade, a void, a universe with no story to tell. But here we are, not just surviving but thriving, in defiance of symmetry. And now, at the end of the road, having passed through the particle colliders, the ghost chambers of neutrino observatories, the whispers of gamma rays and Cold War weapon fantasies, we must ask the question again. But this time not with wonder, with humility, because antimatter has revealed more than a physics puzzle. It has shown us a truth we rarely confront. Reality is not fair. It is precise, predictable, often beautiful. But fair? Numbers somewhere, something broke a perfect symmetry. And from that fracture, everything else poured in. Atoms, light, memory, grief, motion, music. The entire scaffolding of experience built upon a cosmic glitch. That glitch is not just the reason we're here, it is the reason there is a here at all.
And what makes antimatter so haunting is that it's still with us, not in abundance, but in fingerprints, in traces, in lab-made shadows that flicker briefly before vanishing, in radiation bursts from dying stars, in positrons emitted in PET scans, helping us see ourselves from the inside out.
Antimatter is the mirror the universe holds up to itself, and then refuses to look into. Because what would it see? Not just symmetry, but possibility, a different kind of cosmos, a different kind of choice, one where we never existed and something else did. It forces us to rethink not only the universe, but ourselves. We like to believe the universe is elegant, that its rules are eternal, that its outcomes are necessary. But antimatter whispers something else, that maybe the laws are flexible, that maybe creation itself has a bias, that maybe chance played a larger role than we care to admit. When we stare into the equations, we expect certainty, but what we find is contingency. Everything could have gone differently. Every proton in your body is a survivor of a statistical miracle. A particle that should have been annihilated but wasn't. A particle that made it through when a billion others did not. And that survivor built the calcium in your bones, the iron in your blood, the carbon that writes these thoughts as you read them. We are not simply made of stars, we are made of the fraction that remained. But antimatter doesn't just speak of the past, it asks us what else we've missed. Because if something as fundamental as the balance of matter and antimatter was broken, if even the most sacred symmetries can fail, then what other assumptions do we hold too tightly? Is time really linear? Is space really empty? Is causality just a local illusion? Antimatter is the invitation to question everything. It challenges our definitions. If an electron and a positron are indistinguishable except for charge, and both vanish without a trace upon contact, which was real? Was it matter that won? Or was it antimatter that refused to die? Or are they both just expressions of a deeper unity? A symmetry so elegant that it must be broken to be seen. Perhaps we're looking at this the wrong way. Perhaps the universe didn't fail to be symmetrical. Perhaps the act of breaking symmetry was the moment it became real. Maybe perfection is sterile. Maybe only in imbalance does complexity emerge. Maybe life itself is a symptom of the fracture. And if that's true, then we are not a mistake. We are the outcome of the universe refusing to be neutral. We are what happens when nature leans ever so slightly to one side, and keeps leaning. Antimatter also speaks of boundaries and of what can and cannot coexist. It's the ultimate paradox, a substance made entirely to be unmade. It touches and vanishes. It offers no middle ground, only annihilation. And in that harsh binary, we see the fragility of balance, the edge we all live on. Because even now, even after all the equations and detectors and missions and megawatts, we have not solved the antimatter riddle. Not really. We've modeled it, observed it, trapped it, dreamed of it, but it remains just beyond reach, like the mirror you can never step through. It's there, and it's not. And maybe that's the point. Maybe the mystery is the message. That not all questions have clean answers, that some puzzles exist not to be solved, but to be pursued. Because in the pursuit, in the act of reaching, we define ourselves. We are the species that looked into the void and saw its own reflection, reversed. We are the beings that annihilate ignorance with knowledge and build futures from fire. So here we are, at the end of the antimatter journey, staring into the final mirror. And what do we see? Not destruction, not perfection, but paradox. The kind that burns, the kind that builds, the kind that tells us you were not supposed to be here, and yet somehow you are.
It's easy to forget, after 14 chapters of physics and philosophy, just how absurd this all is.
You, me, the stars, the screen you're watching, the language we're using, the neural patterns firing in your brain, and the atoms making up the neurons that fire them. None of it should be here. Everything we've learned points to one terrifying conclusion. In the first microseconds after the Big Bang, matter and antimatter were created in equal measure and annihilated in equal measure. A beautiful, perfect balance. And then somehow one extra particle of matter survived for every billion destroyed. A rounding error, a cosmic miscalculation, or something more. That tiny imbalance is why we exist. Not metaphorically, literally. It is the surplus from a universal massacre, the ash that wasn't swept away. We are that ash, and yet we are also more.
Because in that moment, that improbable tilt, something began. Something fragile, something reckless, something called reality.
When we began this documentary, we asked the question, why is there something instead of nothing?
We've now run the gauntlet of possible answers.
We've explored baryogenesis and symmetry violations. We've chased neutrinos and their whispered secrets. We've searched for antistars and watched for silent gamma flares that never came. We've contemplated engines powered by annihilation and bombs whispered into existence in Cold War shadows. But at the end of this long, winding path, we must return to that question, because we are not the same. We've changed. Our understanding is deeper now, not more certain, but more complete in its uncertainty. The universe's bias toward matter, this quiet rebellion against symmetry, still has no definitive explanation. It may forever elude us. But perhaps the explanation itself is less important than what that bias means, because it means we are not a given, we are a consequence, a remainder, a possibility that was not guaranteed. The cosmos did not need us. The equations did not require consciousness. The laws did not ask for eyes to witness their unfolding. And yet here we are, talking about them, asking questions they never expected to be asked. That is the strange miracle of it. Not just that something survived, but that what survived became curious. What are the odds that the same universe which nearly erased all of matter would also birth beings capable of uncovering that fact? What are the odds that we, infinitesimal motes in a corner of a cold galaxy, would even be able to form the question? The more we learn about antimatter, the more we are reminded that existence is not normal. It is precarious. It is outrageous. It is earned. This is not to say we are special in some spiritual sense, but in the statistical sense, in the sheer unlikelihood of survival. You are a descendant of particles that won a war by simply being forgotten. And yet, here you are, watching this, contemplating shadows older than stars. So what do we do with that? How do we respond to the knowledge that we shouldn't exist? We return to the world, to each other, to the strange glowing reality we call home. We return with a different gaze, one that sees existence not as a backdrop but as a question that never stops being asked. Because every proton in your body tells a story of survival. Every electron you've ever touched, in air, in water, in thought, is a relic of that first improbable victory. We are not the aftermath, we are the continuation. There's something quietly poetic in the idea that the universe's imperfection, its inability to perfectly erase itself, is the only reason we're here to notice. That we are the witnesses of the glitch. And perhaps, in witnessing it, we fulfill something the universe could never do alone. Self-reflection, a perfect universe, one that obeyed symmetry to the letter, would have been sterile, static. It would have collapsed into light, and that light would have expanded into cold and silence. But this one broke the rules, and in breaking them, it remembered something else. To be interesting, that might be the ultimate lesson of antimatter. That perfection isn't necessary, that survival isn't clean, that everything beautiful, including thought itself, may emerge not despite imperfection, but because of it. The universe broke its own balance, and from that imbalance came life, wonder, consciousness, curiosity, and return. We return not to close the loop, but to recognize that loops are illusions, that every ending is a new symmetry waiting to be broken. Every answer, a new question daring to be asked. And so the antimatter story ends not with erasure, but with presence. We shouldn't exist, but we do. And in the vast, cold, indifferent dark, that fact shines brighter than any star. We've traced a ghost across time, from the first flicker of the Big Bang, through the annihilation fields of a newborn cosmos, past colliders and theories and traps of magnetic light. We've followed antimatter to the brink of erasure and found ourselves staring into the mirror it left behind. But now the trail ends, or perhaps it transforms. Because if antimatter is the mirror of matter, then we must ask, what is matter really? We speak of atoms, protons, neutrons, electrons, the particles that build stars, oceans, brains. But these are only scaffolds, abstractions in motion. Dig deeper, and atoms give way to quarks, leptons and gluons, smaller pieces, stranger behaviors. And yet, no answers, only more questions. The deeper we go, the more matter begins to blur. It loses its edge, becomes statistical, probabilistic, less like a thing and more like a pattern. And in that blur, a new mystery begins to whisper. We once thought of matter as solid, immutable, a building block. Then we learned it's mostly empty. Atoms are over 99.9999999% vacuum. Their solidity is an illusion. The resistance you feel when touching a wall is not atoms colliding, but electromagnetic force fields repelling. Nothing is touching anything, and yet you feel the wall, you trust the floor, you believe in matter. But should you? Because if antimatter taught us anything, it's that existence can vanish, that particles are not immortal. They are conditions, fleeting ones, held together by agreement between fields and probabilities. So let us ask one final question. What comes after antimatter? What lies beyond the mirror? Not in opposition to matter, but beneath it. Physicists have long searched for deeper layers. Some believe particles are not fundamental, but made of even smaller constituents, hypothetical entities called prions. Others think that particles are not objects at all, but vibrations in quantum fields, like musical notes in the fabric of space. An electron in this view is not a thing. It's a resonance, a standing wave in a field that fills all space. Matter is not in space. Matter is what space is doing. This changes everything, and it means particles are not building blocks, but behaviors. That matter isn't made of stuff, but of events, processes that occur, patterns that repeat, like whirlpools in a river. Temporary, persistent, but not permanent. It also means that nothing is truly separate. All matter is connected by the fields it emerges from. Electrons here and electrons on the edge of the observable universe are part of the same underlying field, always linked, always resonant. And yet, we experience matter as distinct, you, me, this screen, separate identities, separate masses. But this too may be illusion. Because the closer we look at particles, the more they vanish. A point-like electron has no volume. A quark is never seen alone. A photon has no rest mass. And yet all of these are real because they interact, because they leave traces. Antimatter left traces. But what if there are particles that don't? Dark matter, perhaps, a substance we know only through its gravity. Or axions, hypothetical particles that solve mathematical problems without ever appearing directly. Or virtual particles, which arise from the vacuum, exist for a flicker of time, and return without being observed. What do we call a particle that doesn't exist in the traditional sense, but still affects the world? We call it reality. And perhaps that is where this journey leads, not to more answers, but to a deeper humility. That the universe is not made of things, but of possibilities, of vibrations and cancellations, of moments where fields align long enough to give birth to structure before dissolving again into uncertainty. This view is not comforting. It erodes our sense of solidity. It whispers that everything, matter, antimatter, memory, self, may be transient. But it is also liberating. Because if particles are temporary alignments in an eternal field, then so are we. And in that view, existence is participation, a resonance, a note struck in the silence. Antimatter was one note. Matter is another. But the music continues. So what comes after antimatter? A better question might be, what comes next for us? Because now we must turn the mirror inward. We must begin the second story, not of opposition, but of composition. Not what the universe avoided, but what it became. In our next journey, we will follow matter itself into its strange, layered heart. We will ask, what is an atom, if it's mostly nothing? What is a particle if it cannot be touched? What is reality if the deeper we look, the less there is? We'll explore quantum fields, virtual particles, and the idea that solidity is an illusion cast by probability.
We'll dive into the structure of matter, not to find a final answer, but to learn how something can exist without ever fully being.
Antimatter brought us to the edge of existence. Now we step beyond it.
Thank you for joining us on this extraordinary journey through the universe here on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us each Friday at 7 p.m. Eastern, where we unravel the darkest mysteries of space.